All right, so just to understand the audience, how many of us here are data scientists in the room? All right, a few of us. Data engineers? ML engineers? Okay. How many of us in the room use Python? Oh, beautiful. Thank you. Scala? SQL? Awesome. So the reason I'm asking all these questions is because the topic is simplifying data engineering. It's a very broad topic. The point here is like data engineering is massive, right? So from the point when the data is originated to the point where you capture the data, manipulate the data, eventually go and make it available for the consumers, everything can fall under data engineering bracket. It's a broad topic. I'm going to focus, and I'll keep focusing onto this topic going forward, but we're going to look at this topic from the lens of a data science use case. I'm going to introduce the use case as well, and specifically what are the problems that a particular data engineer, ML engineer would face when a data scientist is actually working on a use case, right? So oversimplified view of the use case. At the top, you have data scientists. They're typically presented with a business problem. When they have the business problem, they look at their first-party data, and then they start enriching the data. So typically, they add more second-party data, third-party data. Eventually, they end up creating more features. For non-data scientists, ML engineers, features are basically columns that you add. There's a lot of feature engineering, which is very similar to data engineering. There's manipulation of data frame operations, tables, joins, aggregations. Eventually, you want to create, and the consumer on the other side, which is when you start wanting to train the model, you want to create one big fat table with all the features. From that point onwards, you would start doing your machine learning stuff. Once you've trained the model, you would then have a model as an output, right? So that's where data scientists, typically, they would stop. So then there's a role of ML engineers, data engineers. In this whole life cycle, they've done a lot, by the way. So they've actually probably gone ahead and they have captured the new data source. Maybe somebody's using weather, somebody's using census data. They would just want to enrich the data set, right? When they're using their notebooks, typically notebooks is what data scientists would use, right? So when they're using the notebooks, they can have data as files on their local machines, or they can have APIs that they would hook onto on their notebooks. They would get all that data. They would then start enriching, this data set, manipulating the data set. But this time, from data engineering perspective, there are new data sources that are getting created. You have to actually build, manage, maintain pipelines so that when they are deploying these models in production for inferencing, this data is actually continuously getting loaded onto the platforms, right? So it's a big challenge. The second thing that's happening is everything that is in the notebook has to now happen on the wider data set. So typically, data scientists would sample the data out. That's what they use. But once they've created these new features or columns, and they use these new columns for training the models, these columns need to exist on the production data set when they're inferencing using these models, right? So a lot of challenges. And if I have to quickly show some of these challenges, I'm not going to go into this because these challenges are solved in multiple ways. But because data is moving all over the place, security governance becomes a big challenge in itself. There are environment issues. Typically, data scientists do not work on the same platform. They actually go and take the data out because they have to manipulate the data. So they don't want to go and give the access to the same tables where a BI report is running or an analyst is running their queries, right? So they don't want to go and change the data, that source data. So there's a lot of data movement happening. Also, from the data engineer perspective, because we are now going to the source, getting the data, maybe doing manipulation initially, all that could be done through SQL. And then when it comes to data science work, where there's notebook that you're probably productionizing, or there's sample code, or the code that is written in Python, you're now switching languages here, right? So you're no longer so there's no one language, right? So you're not using, let's say, Python from start to end. This is, again, a big problem, again, because, again, all of those who raise their hands for both SQL and Python, How many of you are using the same product to run your SQL and Python? So few, right? It's a challenge. Even in the same product, you're probably creating your independent clusters. Let's say you have to run Java and you have to run Scala. Like they are not, like you can't use the same cluster, same runtime environment to run these languages, right? So it's a challenge that you have to solve. And let's see how Snowflake solves that challenge using a product. We call it as Snowpark. How many of us have heard about Snowpark before? All right, awesome, beautiful. So let me put this in context for those who have not heard about Snowpark before. So I'll take you through a journey. Snowflake, up to I think 2018, 2019, it's a SaaS service. It was built to make access or analytical access for the data easier, right? Whether your data is structured or semi-structured. Use SQL, you don't have to go and use surveys, denormalize the data set and all that stuff to, start using for reporting analytical purposes, right? So Snowflake was built so that you can use basic SQL. If you have a JSON file, drop it in Snowflake, just start, querying it, put your Tableau report on top of it. It would work, right? A lot happened in the product in last 3-4 years. We started adding new functionalities. And we also realized the fact that we are now supporting workloads that just do not use SQL. So Snowpark as a project was born out of that requirement. So when I say, and then there are two parts of Snowpark, by the way. So there's client side and there's a server side. When you see SQL and SQL, so Snowflake has a Python connector, right? So Snowflake Python connector. The existing Snowflake Python connector basically creates a session with Snowflake. And what you do today is you write a SQL query in there, right? So irrespective of how you're using or connecting to Snowflake, whether it was our UI, Snowside, or a Tableau notebook, like a product, they would all convert your queries into SQL. So you're writing SQL, and on the server side, which is on the Snowflake compute side, we are running SQL. So that's how it used to be. When we say Snowpark for Python, or Snowpark in general, you see there's Scala, Java, Python, all these languages. We are now talking about native execution of these languages. So when you say Python or Scala, you're actually writing data frame operations. There's no SQL that you're writing on the client side. On the server side, we actually implemented, so that's the reason we have two aspects there, and we'll uncover those two aspects. On the server side, we are actually creating runtime environments for these languages. So when I say Java on server, Snowflake creates a JVM. It takes a jar file that you have created, and it would deploy the jar file on the JVM that is running on the server side. So when I say server side is the compute resource, right? So if you have a small cluster, we're talking about 2 nodes running in the small cluster. And we'll get a little bit more deeper into that. Similarly for Python, we are actually creating a Python runtime environment, and all the open source libraries that you would be using to run your code would be created or would be created as a runtime environment on the server side, and your code would run natively on the server side. So let's see how that is working. So today, because we only have 30 minutes, we are going to focus on Python as a language, right? So what is Snowpark for Python? Snowpark for Python is, as I mentioned, it is native execution of Python. So you're performing data frame operations, you're using open source libraries, and you're writing Python code. To support open source libraries, and also, so the way it's running on the server side, and if you're not aware on the server side, like Snowflake takes security very, very seriously, right? Your SaaS platform, security is something that is inbuilt into the product itself. All our compute resources are sandboxed, which really means that we do not have access to internet. So if you're using, PyTorch, we cannot do as I said, we'll be creating a runtime environment. We cannot do pip install PyTorch. That's not going to happen because there's no internet connectivity there. To make that happen, last year Snowflake invested in Anaconda, and we partnered with Anaconda. So what we've done is we've created a channel. It's a public channel on Anaconda, and we'll deep dive into that as well. But we're using that to provide access to all the open source libraries that are up there. So we use that channel to then create the runtime environment on the server side. Yep. So let's look at client side first. A very easy way of differentiating between client side and server side is that client side is data frame operations, pure data frame operations. It's an API, and under the covers, what you see here is it's a very simple data frame filter thing that I've written there, right? So you just do dataframe.filter, provide the value, you're doing an ag on top of it. So it's no longer a SQL statement, it's not select star from table where blah, right? We're not doing that anymore. Under the covers, there is this Snowpark package. You can do pip install, it's available through the channel, but it has two components. It has our existing connector for Python, which we use to create a session to connect to Snowflake, and it has a query translator service. Now this query translator service takes all the functions that you're using in data frame operations, and under the covers is actually converting that into SQL. So you as a consumer, it's transparent to you. You're writing data frame operations. When it executes on Snowflake, we're actually converting that to SQL. What are the benefits of that? Biggest benefit that we get is that we can parallelize the execution of data frame now. So this is big for those who understand data frames, work with pandas data frame. It's not a trivial job to parallelize your data frame operations, right? In Snowflake, any data frame API operation is 100% pushed down. So nothing is brought back into your IDE unless you really want to bring it back into the IDE. So it is possible, but it's not something that would be done by default. When you write your data frame operations, under the covers, they go down and they execute in parallel across the clusters that are spin up in Snowflake. So if you're using, let's say, a medium cluster, you write a data frame operation, it just gets distributed across all the clusters. Second big benefit is that we actually go and optimize the execution of this data frame under the covers. So it's a lazy execution of data frame. You write your code and you perform any kind of operation on the data frame. That is the time when we take the DAG that we are building under the covers, and we then execute it, convert it into SQL. So we do two things. We convert it into an optimized SQL, and we also bring it through our services layer. So we create an optimized execution plan. Now, the benefit of that is that you actually do not have to even go and execute the data frame to see what is going to get executed. So you can actually use explain capability on the data frame to actually look at how that data frame would get executed. So again, it's very, very easy. Let's say there's a massive table. You're doing data frame and you're reading the table. And the next step itself, you actually want to go and filter some data. So in pandas data frame, you require a machine or a RAM that would take all the data, that will hold all the data in the data frame before you filter the data, right? In Snowflake, Snowpark data frame, when you do explain plan, it'll tell you how it's going to go and scan the tables under the covers. So once you know how the scanning is working, and if you've missed out that filter, you can actually go and update your code even before you execute them. So it helps in optimizing how you're going to run this operation under the covers. What about, so as I said, this was all data frames. What about all the third-party libraries? The reason why we all love Python is because of the open source third-party libraries. And we would be really stupid if you try and even convert that into SQL, right? So nobody should do that. I don't know if they would do that or not. So this is where we have a different pattern. And this is the server-side execution of Snowpark. In this example, there is a function which is, it's calculating distance. It's using GeoPandas library under the covers. 2 points, call this library, calculate the distance between. Fairly simple code. But instead of using a query translator service, now we have something called object serializer in the same package, right? When you create this UDF or user-defined function, we take the code that you have defined in this user-defined function. We use Cloud Pickle under the covers, so we pickle it, we zip it, we drop it into Snowflake. So it goes into a Snowflake stage location. So there's an object that gets created. There's also a metadata definition that gets created at the time of defining the UDF itself, right? So we have an object, we have the metadata definition. At the time of the call is when we create this runtime environment. So what you do at the UDF level is you, at very high level, specify, I'm using GeoPandas, I'm using pandas under the covers, and I want to run this code. Snowflake actually goes And when you call this this UDF, we actually go and create a runtime environment. At the highest level you have specified your libraries, we actually go and get all the dependencies that are required to run these libraries to create the runtime environment, and then we run your code under the covers. So all this is happening at the time of the call. It's very, very easy to forget that it is still the same compute resource. Also, we don't reserve the whole compute resource. It's only the code that is going in there. The second thing is that this code itself also gets automatically parallelized across all the nodes. So in this example, it's not that very intuitive because here you only see one single node, so an extra small cluster. But let's say it's a medium cluster. This runtime environment gets created in every single node of the cluster. So your code automatically gets executed in parallel. You don't have to do anything about it. Now, not everything gets parallelized. If you're doing model training and it's a single node activity, like you would not get benefit by creating, you're using a medium cluster, right? So you would still require a single node. But anything that would benefit from parallelization, so typical scalar execution of your code, that would automatically get distributed under the covers. So more on Anaconda. There are 1,300 plus libraries, different versions of libraries on Anaconda channel right now. We keep on adding these packages, but you can see most open source packages are available on this Anaconda channel. It's a public channel. It's available for both client side and server side. So you can use it if you want to use it on the client side. Your client side ID, it's pretty ID independent. So you can pip install Snowpark for Python, right? Or you can just get it through the channel. It's available on the channel as well. So you're free to use PyCharm, VSCode, Python notebooks, hosted notebooks, like anything that you want. Because end of the day, once you start creating data frames and UDFs, everything is 100% pushed down onto Snowflake. We use Conda Package Manager to actually then figure out all the dependencies. So that is another big problem with Python, right? As in when you move between environments, a data scientist could be using a notebook. They could be using a different version of Python. You could be using a different version of the library itself. When you take it to dev environment, it might not match there. The dev environment may not match with the UAT environment, and prod environment could be on a completely different version of libraries and Python environment. This is all managed by Snowflake. So when you use Snowpark for Python, we actually just curate the environment for you. So we only need at the highest level the version of the libraries, and we'll make sure that all the dependency requirement is managed through our package manager. We also have SQL integration now for all the people that like SQL, but also from the perspective of automation. You can bring pure Python code. So there might be stuff where you do not, if you have a .py file and you're using functions from the .py file into the UDF, like you can bring all the external code. If you're using a library that is pure Python, but you can't find it on Anaconda, you can bring it from external code from there, and then you can package it as part of a function. Again, it's a simple SQL function, but under the covers, you can just bring all that and run that on Snowflake, again, in the same exact pattern. We're going to do a demo as well, and hopefully the demo works. But I'll quickly summarize this, right? What you see on the left-hand side that we call as DataFrame API is where you're writing DataFrame code, we're using a query translator service, and we are converting that into SQL. And this is by default parallel execution of your data frames. On the right-hand side is everything that requires third-party packages. We create a user-defined function or stored procedure. There are two objects that you can create. We will package your code. We will drop that code into Snowflake. We would create the runtime environment based on the libraries that you have specified, and we would run that code on Snowflake. Again, everything is parallelized by default on Snowflake. So again, a lot of talk. Let's actually look at the demo here. All right, so I have a library. I have a Python notebook. Under the covers, I just created a Conda environment. I'm going to quickly go and bring in the libraries. I'm just creating a connection to Snowflake. This is where I'm using my our existing Python connector. Once that is done, we would just want to actually look at a table that has some data in Snowflake. So the use case is advertising spend. We have this campaign data with us, some 300,000 rows. We want to understand so a marketing manager, we want to understand if I adjust my spend across the channels, how my revenue would get impacted. So we want to build, that's a use case, and we want to build a model, and we want to actually showcase that as part of our requirement, right? So we quickly go and run this quick query, right? So this is, as you see, this is basically a standard data frame operation. I've done some group by, I've done some aggregation. I'm trying to find out by year, month, what are the channel and total cost. Yeah. Actually, it will be good to see, as I was saying, this is 100% push down operations on Snowflake. All right, I did not get logged out. So if I look at the query history there, you would see that that data frame operation actually got pushed down and a SQL query was created under the covers, right? So everything was happening within Snowflake itself. Let's pivot. So again, you can use third-party library. You can also use functions. As I said, this is a default function that is available in Snowflake. You can quickly pivot on the channel. So instead of using one-hot encoding, we can quickly do this. And then I'm going to merge my revenue information, which is another table that exists on Snowflake, and what we just created as part of basic data frame operation. So now we have a manipulated something that our data scientists would do. We have combined two data sets, and now we have all the features that I would use for training a model. As I was saying, you don't have to execute these queries. So if you just run .explain on the data frame, you would see there's a code. It's not pretty, but it is what my Jupyter notebook is showing. And you would see a DAG, or in fact, the explain plan that you can see here, right? So I can see that my table scan is going to happen, that I'm going to run so there's a push down bloom join filter that is going to reduce the number of partitions that I would be reading from my table. And you can see total number of byte scan, table scan. So a lot of information. It would help you, especially when you're dealing with very, very large data sets. So I should have mentioned this. If you can fit your data in memory, don't even bother about these things. This is not for that use case. This is for use case when you have gigabytes, terabytes of data, you're manipulating large data sets. You do not, and sometimes you cannot just move that data out, right? It's not just for data engineering, feature engineering, but also when it comes to scoring of data as well. Because when you're running inferencing, especially when it's large volumes of data, sometimes you can not run intraday inferencing just because your data volumes were so large, right? So we'll talk about inferencing as well. So what I'm going to do here is I'm quickly going to go and delete some null values. Again, this is something that a data scientist would do. They don't want null values in the data set, and we're just preparing the data set. So in this code, I'll run this code, and I would quickly define a model. In fact, So this is a model, right? It's a code for model. I'm gonna actually go, and you can see I'm using sklearn. I'll be doing linear regression, and I'll be performing certain operations. And we'll quickly walk through the code, what that is. So there are certain numeric features. Because this is gonna be used for training a model, and because third-party libraries, or all open source libraries that you would use, they require data in pandas data frame. So I can't use my Snowpark DataFrame, right? So in this scenario, I can bring the data back by just saying .2pandas. So .2pandas is actually going to go bring the data back, and now my DF is a pandas data frame here, right? From that point onwards, it's fairly simple, right? So you can just create some features, build some transformers. I'm creating a pipeline here, so I'm using the sklearn pipeline feature. And then from that point onwards, I've just defined a pipeline where I'm going to run a preprocessor and a linear regression classifier. Train test split, quick grid search, so that, lazy way of actually training a model. And then we'll fit a model. Once the model is fit, I want to take this model and take the the model object and drop it into a stage location. So I'm going to create the model object, and I'm going to write it out into a stage location there, right? And then return the training value. So this is good. I want to quickly test this. This is all running in my local here. So I've quickly trained the model, and I can see that my R2 score and everything is good. Now, the data actually moved into Snowflake, into the local machine that we have, right? Let's say now I want to actually go and run this training on very, very large data set, which cannot fit in my local laptop. For that, we would create a stored procedure object. Now, this stored proc object is actually encapsulating my function that we just created to train the model. And at very, very high level, we are telling Snowflake that I'm going to use Snowpark Python. Why I'm telling Snowpark Python is because we read the data into a Snowpark Python data frame, and then we actually did .2 pandas to it. So I'm accessing data that is within Snowflake. I'm going to be using scikit-learn and joblib libraries. Like very, very high level, what are the libraries I'm going to be using? So this has now created a stored procedure object in Snowflake. Now this stored proc object, it took a little bit of time. The reason it took a little bit of time is because it has taken the code. So it's right now doing a lot of things. It's taking the code, it's getting all the dependencies, it's packaging the code, and it's now dropping this into the stage location. So what we were doing in the UDF is what is happening with stored proc as well. So to train the model, now when I call this session.call, right, and when I call this stored procedure object that we just created, this is 100% push down of training on Snowflake. So you can actually quickly go back to our query history, and you would see that the last query that got executed was a call of this function. So you can run really large-scale training jobs, and these jobs would execute where the data is. You're no longer moving data between platforms. And what should have happened here as well as part of the code is that we would have So we should have the model object as well. So that's the model object that got dropped into the stage location. Once that is done, I can quickly go and create a UDF. So a user-defined function. I'm calling this model object, and I'm going to be going and writing it back into Snowflake. So this is the UDF definition, and then from that point onwards, I can use that for scoring. Now this scoring, because it's a user-defined function, it is not dependent on a language. This is available for SQL users because it's a function, end of the day. You just specify the inputs, and you get the output. This is good. You can call this in batch fashion, and you can score really, really large data sets. Data is not moving. In fact, what we have done is we have deployed the model next to the data instead of taking the data to the model. But this is not where the value is. Like, what else can you do? What I'm going to do, and quickly, this is a little bit off topic as well, is what if I can create a dashboard, and I can give this dashboard to my marketing managers, and we would use this dashboard for interactive call of this UDF, right? So this is a Streamlit dashboard. Snowflake acquired Streamlit. It's an open source Python-based visualization tool. Like, it's very, very good. You just write basic Python code, and you can come up with any kind of visualization that you like. This is built on Streamlit. What I'm doing here is there are a few sliders, which basically tells, it's the same input information, how much money you would want to spend. And let's say I want to increase my social media spend. Under the covers, this is now calling a UDF, and it's going to give you, or give marketing managers, real-time insight onto how much revenue that can be predicted. Now, this is where the actual business benefit also happens, right? So apart from the batch, scoring of data, this is where, a lot of business benefit would come through as well. I would want to take a few questions as well. We are running out of time, so I would quickly take some questions. Any Q&A?
Awesome. Round of applause for Rishu.
Thank you.
If you go back to your function where you train the data set,
Yep.
I wanted double check if I'm going crazy, but it seems to me that there is a function that has a lot of side effects. Inside the function, you're actually importing new libraries and you're writing files to somewhere. Where does the file go?
So file is, I was showing, so when I showed you, when I ran a query on Snowflake,
Yep.
that file goes into an internal stage location. So internal stage location is, so under the covers, Snowflake actually uses the object store of the cloud provider, which is managed by Snowflake.
Yep.
So I'm creating that model file, I'm writing the model file into that location. So it's outside of a compute resource, but it's within the storage layer of Snowflake.
So we'll also have to have the data scientists who are writing functions, that training function, for example, will also have to have a model of the computational model that Snowflake's actually running, right? In order to actually figure out.
To train the model?
Like, no, as in, think about it, right? You've got, everyone's pretty familiar with how functions work, how computers work in a local machine. So as a data scientist, I would have to also import your environment, the Snowflake model of computation into my mind as I write that sklearn function, right? I'll actually have to understand how everything works in Snowflake in general.
Okay, so
right?
Yeah. So this is where the server-side execution comes in play, right? So the file was in a stage location, but we also defined a user-defined function on top of it, which is calling that model as an object.
Yep.
So in this scenario, your model is nothing more than a function, which is taking some inputs.
Yes.
It's giving you model.predict as an output.
Yes.
Yeah.
I followed it much.
So all that is running in this sandbox environment.
Yep.
Which is a subset of the existing compute resource. So it's not taking the whole compute resource, it's taking a subset of the RAM.
Right. So when it comes to debugging your functions then, you will have to figure out, you'll have to know, essentially, you're running your function on someone else's computer, right?
Yes.
And you'll have to know what the underlying architectures of that someone else's computer is when you need to debug your functions.
So debug the code or debug the compute? So compute is self-managed. Code, we would write the output of the Python code into a location that you can actually go and read the errors that would come through. That's basically nothing more than what you would see in a notebook, and you get to see that.
Awesome. Well, thanks so much, Rishu. Sorry about the grilling, but you did very well and really good questions, Chewy. Thanks so much.